talk. Okay. I just want to thank everybody. It's a great opportunity. We got together here at a wonderful occasion, and I came up with this idea. Any good activities need to be promoted, and since this is a wonderful group, I thought it's wonderful to have something to just unite us and just celebrate. So I actually started this idea, and I'm very sorry that we really didn't have much time to prepare in organized fashion. It's really disorganized, but we got T-shirts, and this is actually $10 except double X what do you call it, double XL. That's $12. Any actually profit from this is going to be used, to benefit the group. Maybe, most likely, just help the food operation. So chances are you're helping the group, and just we're gonna actually feed you. And I like to tell you about this, since some of you going to wear the T-shirt, and this group need to be more promoted. I think it's a wonderful group. And we are in the heart of the Silicon Valley. I came up with the business card. It's to help us, and since you're wearing a T-shirt, maybe some of you going to be asked, what is Silicon Valley Fig? And then just graciously ask them, are you into computers? If they're actually into computers, just explain what we do, And if they're really interested, just give them this, hand out this, the business card. It's here. Please take, whenever you, have time. And we only got 250 of this. I'm going to just leave it here. But, just explain what we do. And make sure, we actually, meet every month. So check our website, mention it. So that's actually what I want to say. And lastly, I want to really, say that there's 4 individuals really helping this group. Without these 4 individuals, just we don't have meeting, here. So I just want to, name the person: Kevin, George, and Dave, and Ting. Without them, I have to give Ting a T-shirt. This meeting just won't happen. And so, since I started this, I decided to give them this complimentary T-shirts for them. I think it's acceptable. And later, of course, we're gonna present this T-shirt to Chuck. That's all actually I want to say for now. Thank you. Okay.
As Masa mentioned, Ting has sustained us for 4 years. Care to think about the gift to Ting. I don't know that. For more than years than I'd care to think about Ting. As program chairman himself for many years, and certainly giving more talks than there have been meetings. Anyway, without further ado, CHA.
Okay, so for those who has not been with us, this project has been going on for almost a year now, since January this year. And so I was keep on saying, well, let's build a 14C. And for half a year, I couldn't do it. And it was just terrible. I look back. In July, I had bypass surgery. So on the sick bed, I got lots of time to think. Why it took me so long to get this thing done? And it has been 6 months since. So the way I thought was that the conclusion was, okay, this is the goal. We just want a very simple Forth system that can be compiled by a standard C compiler. It's going to be portable to microprocessors whose manufacturers provide C compilers in their development tools. Lots of them do now. So it's a good idea to have it available in C so that the standard compiler can handle it. Well, the fundamental problem, as I realized on my sick bed, was that the C compiler was designed specifically so that it is impossible to implement the Forth on it. Okay, and that was my problem. Okay, two things in the C compiler which does not want you to do. One, you cannot write into code space. Code space, wherever it resides, is sacred. Okay, you cannot touch it, but we want to touch it. And then C gives you lots of code space, lots of data space, and you are not allowed to execute code from the data space. Okay, sorry. So with these two restrictions, basically you just cannot write a Forth program in C. Okay, so you have to cheat. You have to go around the restrictions, and that was the problem. To write a good Forth program in C, my estimate is that you need 10 years of experience to program in C, day in and day out. And you fill all the corners in the C compiler, find all the loopholes, all the bypasses, and then you probably can do it. But with what I was trying to do is to acquire that kind of expertise in a 6-month period. And it is not quite possible because I don't have the affinity. I'm not in love with any of these C compilers. So without that really love or a drive to learn everything about it, it is very difficult. So that's why it took so long. Okay, so if we want to design a Forth using the C compiler from ground up, so what do we want? How many Forth words? How to interact with the operating system? How to interact with the user? 16 bits, 32 bits, direct threaded or indirect threaded, token or subroutine threading. All these are the problems you would ask yourself when you implement Forth. So we do have lots of quite a few Forth written in C, and I don't know if I had looked at them all, but I looked at a few of them. They are all too complicated. The simplest Forth, as it claimed, runs about a couple of megabytes in source code, and there are too many words. And usually, the writer of a C Forth in C compiler is an expert in C and Unix, so it tries to conform to the Unix system and try to include lots of functions that's available in the Unix environment, and that makes the Forth really complicated. Although they claim to be very simple, if you look at the source code, it's pages, pages, pages after pages, files, 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 files after files, and it's impossible to understand. The one I look at in detail is this Forth. So because we knew the author, we knew he's kind of crazy, but he's still understandable. But this fourth is also quite impossible to understand because it goes outside of C compiler. It uses M4, which is a translator. And because he could not do things in C, so he uses M4 to try to force C to do what he wanted. And it makes, so you, on top of C, I have to learn another language, which is not an easy thing. So finally, I realized that when I was sick, with the heart still trying to move. And Force dictionary is actually just a data structure. Okay. You need to implement all these things are very, very common in Force. So Force dictionary, it is a collection of data structures. Each piece of data has 4 fields. Okay, so you filled in these fields, and you got and link all these things together. You got a Force dictionary. Force dictionary can be constructed outside C compiler and imported as a data array. And this is what you have to do the cheating. Okay, because C compiler, as I understand it, do not want to do these data structures. C can do the data structure if you have a fixed length. And if the data are kind of uniform, but in the Force dictionary, we have name field, which is a field, variable length, and you have parameter field, which is word field, variable length. C especially don't like variable length fields. Okay, if you have fixed field, perfect. Okay, that's trivial. Okay, so what all you have to do is to implement a virtual force engine. You can write that in C trivially. Okay, so the force virtual machine is extremely simple and it's trivial to write in C because C has all the supporting functionalities to support that kind of activity. So interpreter is very easy to write. Trouble is to write compiler. So the virtual force machine, it would interpret the virtual code, and which I think we could use bytecode. And there's lots of things which are done in bytecode. So we can do it that way too. Okay, the virtual force engine. The virtual force engine, when you program all the primitives in Force, in C, and you can build an execution table, or you can use a switch structure to call all these functions. And if you choose to represent the Force words in byte, then you can just give them a bytecode to the virtual force engine, and the virtual force engine would execute. So this is no big deal. So in this project, I did 2 implementations. One uses only 32 bytecodes, and the other one uses 64. It's all more optimized. Well, 64 bytecode. The reason was I just steal all this code from Will Baden's this Forth. So he had implement lots of these words, and I just picked 64, which looked real nice. But since I'm using bytecode, so this virtual force engine can be expanded to 256 bytecodes. So, we probably can do Java with Okay, this I'm using the EP32 chip design as the model. So uh, it is a real machine. It is real CPU, has real instruction set. And I've done lots of work, built a simulator, assembler, compiler, simulator, and everything on top of it. So I just picked that one and use it as the basis to do the C forth. And I use 32-bit words. No reason to go back to 16 bits. And each 32-bit word would contain 1 to 4 byte code. And they are executed from left to right or right to left, however you want to arrange the bytecode. And data stack and return stack are only 32 levels deep. You don't need anything deeper than that. Data stack and return stack are connected to top register. So the top register, the top of data stack is register. So it's from all our experiences, if you catch the top one register, the fourth engine is nearly optimized. Okay, so this is the virtual fourth engine in C. Very simple. There's nothing. So here you initialize all the registers, all the stacks, and specifically you initialize the P to 0. So the program counter counts from the beginning of your data space. And you just fetch, okay, here you, because the data structure has byte data in it, has word data in it. So if I just use this aliasing, then it would read from the same data space. You can read bytes out of it, or you can read words out of it. So, and so here I use phase clock. So clock is a register. It is a register. It is counter. So every time it increments, every time you execute one bytecode, it increments it. And since I have 4 instructions per word, so the phase clock I use, at least 3 bits to count the bytecode from each word. And when you pick up one word, you have 1 to 4 instructions in it. So going through this switch, your case 1 is doing the fetch and decode. And once you fetch and decode these 4 bytecode, you can execute. In the next clock, you execute 1. In that clock, you execute 2, 3, 4. After you finish all these are basically empty. There's nothing there. So it would jump, it just go break out the loop and increment the clock and go back again. So every time you do a jump, you basically reset the clock, reset the 3 bits, 3 least significant bit. So the phase becomes 0. And then you go fetch the next word. And then you go off to these 4 words. So this is the virtual fourth engine. To support this thing, you need a data structure. And this data structure is allocated as a data array. And normally it's treated as a byte array. But in many cases, when you have to read words, you can read words of it. So the fourth dictionary, this is the crucial point of the implementation. You declare a big array, 16 kilobytes, 32 kilobytes, 1 megabyte, whatever. And you just stuff into this data space records and link all the records into a single linked list. And list have records. Each record is a representation of a word. And in this record, you have a link field, which constructs the link list. And you have name field, which identifies which word it is. And you have a code field, which is actually gets executed by the virtual force engine. So every time you give a word to the virtual force engine, you actually give the code field to it. And it just go in and pick up the bytecode and execute that. And whatever happens depends upon what you put in the code field. Okay? And then if this word is a primitive word, it is a low-level word, then you only have the code field. And code field can be as long as you like. And you just stuff bytecode into this field. And if you have a high-level word, and the code field would do a do colon. Basically, it's you want to call another list, okay? And it has the proper mechanism to save the pointer to the current list and then jump to a new list. And the parameter field generally is filled with a list of addresses. Okay? And this is basically the basic structure of the directed threaded force system. Okay, here I'm showing you the beginning, not the beginning of the data field. The beginning of the data data structure is jump to code. That's a colon definition. Okay. Jump to code. So in the code, it initializes all the force stuff and then start the interpreter. And this is where the primitives start. So here, this first word has a link field, which is a 0. So that says this is the beginning of the whole thing. So every time you search to that cell, you know the dictionary has been exhausted. And the first word, that's the, I think that's the by. So you can jump out of the operating system. It has 3 bytes in the name, and then 3 characters in the name field. And this one is the code field. And because this is kind of a user variable, I think. So it's not a by. So it's a user variable. So 04 is the one which will pick up this thing and push it on the stack. And 20 is the return. Okay. So this would just pushes a constant on the stack. And 80 is the location where the first user variable is stored. And so here, this is the first word, and this is the second word, which has a 204, which points to this cell, and that's the link list. And there's another word with 4 characters. So you have 1, 2, 3, and 4 name, and 0 field to the word boundary. And another one which calls the next user variables. Okay. So this is how this thing is constructed, how the dictionary is constructed. And the link field, I think everybody knows all these things. Let's just skip all this. And in this implementation, I follow exactly the E-force model, okay, faithfully. So I got the 218 words. And it's direct threading, and I open 16 kilobytes for the dictionary. Actually, it only needs about 9K. You can play with the rest of the data space. And let me see. Okay, so this dictionary, as I said, it's impossible for C does not like to do it. And if you want this kind of structure, you have to construct it outside of the C compiler. So I'm using eForce meta compiler to construct it because it's exactly the same thing that for EP32. The only difference is EP32 we have 6-bit code, okay, and now we have 8-bit code. So very easy to modify it. Okay, two implementations. One has 32 bytecodes, and the other have 64. And from the outside, you really don't know. You don't need to know, because whatever you do, you can implement words either in low level or in high level. The only difference is the speed. Okay, so here is the demo. We have, I think I would only demonstrate to you the eForce AF, which is the metacompiler, which compiles the generate copy of the eForce dictionary. And then I go to the C compiler, copy this whole the whole data array, copy it in the C program, and then I use GCC to compile the C system. So the demo will compile eForce and exercise eForce and do all these nice things. Okay, let me go to the other places. Okay, here is the okay, let's skip this. You all know how eForce metacompiler works, right? Okay, so let me just get out of it. I'm in the SIG-Wing, and then if you can see, I can call up the GCC. So that's one. GCC eForce _ 11.c. So it just compiles the thing, and /a executes it, and now we are in the in the eForce. If I do words, you see it has only 200 some words, very simple. And if I do a 0, 100, dump, hope it still works. Okay, this one shows the beginning of the data structure. And in the data structure, you can see I have a 6. First word is a 6. This is a do call. So I want to execute a new high-level word. And then this is the address of the high-level word, 20C4. So that's the code. And when you start from the beginning, you really don't have, you are not executing anything. You don't have a list. So when the IP is 0. So you just push that thing onto the return stack, and then replace IP with this instruction, and then go execute, fetch a word, and start executing from there. So that's the, this is the, and then here, this is the area of the user variables, okay? And the next area is the terminal input buffer. So these are all very standard eForce stuff. Okay, let me see if I have anything else to say here. Okay, conclusion. Let's. This guy is by far the simplest thing. I think the whole thing has only, including all the source code, all the eForce metacompiler and everything, has about 20K or something like that. So if you take the time to understand the meta compiler, it's very easy. Lots of room for enhancements. This is what eForce is. So you can actually take it, put it onto your system, microprocessor or whatever, and you have lots of room to add new words and do new things. So what I need is those of you who are really experienced C programmers to help me see how to generate this data structure natively. Okay, so if we can force the C compiler to build this linked list with variable name field and the variable parameter field, then everything will be in C, and we don't have to go to meta compiler or something else outside of the C compiler. Okay.
What's the title say?
Yes.
It's a Chinese curse.
Yeah. No. You hit here to add a title. Okay. Okay. Yes.
What's the difference in performance between 32 primitive and 64?
About a factor of 10. Yeah. So if you actually do everything in C compared to a native fourth written in assembly, so the speed is a factor of 10.
What is the advantages of compiling the dictionary data structure in C rather than using a meta compiler?
Well, it's just that the meta compiler is another language you have to learn. Okay, if you can call all the C functions, or you know all the loopholes, and if you can write everything, make the C compilers to spit out this dictionary, then you don't have to go outside. GCC is all you need. Call GCC and you have eForce.c. Done. Okay, so it's just that yes, John and I talk about how to build this data structure and all these things. Doesn't work, okay? So I need you to sit there and really, to see how using all the functions available, all the tools available in a C compiler, in a GCC compiler, to build this kind of structures. Yes. Yeah.
But one of the things I noticed, if you call GCC directly,
Yes.
probably be a better thing if you, I can show you how to do it, is to have a makefile.
Oh. Makefile is another language, okay? You better get and lots of makefile. I just couldn't understand them. I don't understand. I don't know why they have to go through all these troubles.
Well, the reason being is right now you don't get, because usually I assume you have like one file.
All you need is one file.
When your project is bigger and bigger, you start going to multiple files.
Yeah.
You go, oh my God, which one did I compile this or that?
Yeah, what I want to show you is that, yes, GCC, you call only one file and the work is done, okay? You don't need to do to go to the make.
There are some defaults with the main file, and I try to do it.
Yeah.
More languages
Yes. Yeah. Okay. Yes.
Yes,
John.
talking about before, I noticed that you talked about array, which, where you have to do it in the
Right.
federal language.
Right.
I was thinking that, well, you just build up the array C using the smallest data element, data type element possible, and you have full control
That's what I need, okay? Somebody who knows that, okay? But so far, the problem is that if you, as I say, if you declare a data structure of fixed length, and you can put, byte field, word field, and all these things, and assign them, and then you can just use that to build more data structures. But variable length, byte field, mixed with variable length, word field, oh, see, you don't want to do it. You can't do that, okay? Nobody wants to do that.
Did you consider using other languages for which systems are available in various environments like Python? I don't know what would be a good one, but I'm just wondering if maybe it would be easier in another language that is also had implementations to
Yeah.
he's trying to bootstrap it up on Windows
Yeah.
or something. I don't know.
Yeah, M4.
M4.
Yeah. Okay. You don't want to learn that. Okay. And so is for every other language, yes.
So does it run its own meta compiler yet? Does it run the meta compiler yet?
Well, it's simple. The meta compiler, it's simple, so you can just put it on top. But the thing the complication that most of the force systems has to deal with is a file structure. Okay, so when you are implemented the force in C, all the implementers wanted to put file structures into this, and that just blows up the whole system. Okay, and what I want is avoid that. And so you only have the terminal input, okay? But just with the terminal input, you can import lots of data. And from that, I think in many of the applications I did, meta compiler was such a thing, which is in a file, you stream it through the terminal, and you got your meta compiler, okay? Yes.
If I may, a philosophical observation. The invention of computers by von Neumann was that code could fit in the same memory as data, and it was simple. And I just see Unix and C has done such a job of keeping them separate, and you have returned to simplicity.
Yeah, yeah. The theme, the principle is that all the languages and operating systems is that the users cannot be trusted. Okay, the system has to be protected at all cost against any user.
Well, not users, programmers.
Well, users cannot be trusted either. Okay. Okay. Thank you so much.